Hello students. So let us continue with our discussion on the least upper bound, greatest lower bound and some related problems. So this is the exercise number 17. Let A and B be two non-empty sets such that A less than or equal to B for every A inside A and for every B inside B. Show that supremum of A is less than or equal to the infimum of B. That means every element of the set capital A is less than equal to every element of capital B. In that case, the supremum of the set A is less than or equal to infimum of the set B. Okay, so how to prove that part? Okay, so it is given that A less than or equal to B for every A inside A and B inside B. So if you keep this B fixed, means if you consider one B inside capital B, then what we can write? We can write that A is less than or equal to B for every A inside capital A. So for each B inside capital B, we have A less than or equal to B for every A inside A. That is, B is an upper bound of the set A, but supremum of A is what? It is the least upper bound. So what should be the relation between supremum of A and B? So we should have supremum of A less than or equal to B. But B was any given element inside capital B. That means ultimately what we see that supremum of A is less than or equal to B for every B inside capital B. Take any B inside capital B, it will satisfy this condition, right? So from this what we can see that supremum A is a lower bound of the set B. But infimum of B is what? It is the greatest lower bound of B. Hence, what should be the relation? Supremum A is any lower bound and infimum B is the greatest lower bound. So the relation is supremum of A is less than or equal to infimum of B. And so that's what that was quite simple. So this is another problem which is very important. It will be used in the next semesters also. When we do Riemann integration, this particular result will be very useful. So it is also taken from the book Bartel and Sherbert. Let A and B be bounded non-empty subsets of R and let A plus B, so that's how we define the sum of two sets. A plus B is defined as A plus B, where the first element A is from capital A and the second element B is from capital B. We have to prove that supremum of A plus B is same as supremum of A plus supremum of B, and infimum of A plus B is same as infimum of A plus infimum of B. Okay, so we prove it for supremum, and proving it for infimum is very similar. So I leave it as an exercise, so you please try to do it yourself. So first of all, we have A less than or equal to supremum of A for every A inside A, because supremum is the least upper bound, so it is one of the upper bounds. And small b is less than or equal to supremum of B for every B inside capital B. So if you add them up, A plus B will be less than or equal to supremum A plus supremum B for every A and B inside, for every A inside A and B inside B. That means this quantity supremum A plus supremum B is an upper bound of the set A plus B. But what is supremum of A plus B? It is the least upper bound. So what should be the relation? Relation should be supremum of A plus B is less than or equal to supremum A plus supremum B. So let us keep it as equation number 1 in equation 1. Again we have A plus B is less than or equal to supremum of A plus B. By definition of supremum, it is one of the upper bounds. So again you do the same thing here. For each B you consider what is the what happens to this A. So for each B inside B we can write A plus B is less than or equal to supremum of A plus B for every A inside A, right? So for the time being you keep B fixed. That means A less than or equal to supremum of A plus B minus B for every A inside A. That means what we can say? We can say that this is an upper bound of the set A for each fixed B. But supremum of A is what? It is the greatest, it is the least upper bound. So what should be the relation between them? Supremum of A should be less than or equal to supremum A plus B minus B, and this is true for every B inside B. So we change the sides of B now. So B is less than or equal to supremum a plus b minus supremum of a for every b inside capital B. So since this is true for every b inside capital B, we see that this supremum of a plus b minus supremum of a, it is an upper bound of the set capital B. So it follows that supremum of this is the least upper bound, supremum B. So least upper bound is less than or equal to this. Just change the sides. We have supremum of a plus supremum of b less than or equal to supremum of a plus b. So from 1 and 2 we can conclude that supremum a plus b is equal to supremum s plus supremum b. So the proof for infimum is very similar and is left as an exercise. So please try to do it yourself. Next we have another important result, that is the set of rational numbers is not order complete. That is, a non-empty bounded above set in Q may not have the supremum in Q. Okay, it will have supremum in R, it may not have supremum inside Q. So we need to find at least one such set. So in the and if we can find such a set, we can conclude that the set of rational numbers does not have the completeness property. So set of real numbers has the completeness property, that is a fundamental property of the set of real numbers, right? So here to prove this, so we will follow the Bartel and Sherbert proof. Let T equal to the set of all those rational numbers which are strictly whose square is strictly less than 2. So clearly 1 is an element inside this set because 1 square is less than 2. So this set is a non-empty set. Also 2 is an upper bound of T because if x is greater than or equal to 2, then x square is greater than or equal to 4, and this implies that x does not belong to T, because which elements belong to T? The elements for which x square less than 2, only those elements belong to T. So whenever x is greater than or equal to 2, it implies that x does not belong to T. So if you consider the contrapositive, the equivalent way of saying this is x belongs to T implies x is strictly less than 2. Because whenever x is greater than or equal to 2, x cannot belong to T. So x belongs to T means that x is strictly less than 2. That means what? Every element of T is strictly less than 2. That is, T is a non-empty subset of R that is bounded above. Okay, so 2 is an upper bound. So by completeness property of R, T has a supremum in R. So let y equal to supremum of T. Let y be the supremum of T. Now by law of trichotomy, exactly one of the following is true. Either y square is strictly less than 2, or y square is equal to 2, or y square is greater than 2. So let us consider the cases one by one. If y square is less than 2, then consider the number y plus 1 by n, where n belongs to natural number. So y plus 1 by n square is what? Y square plus twice y by n plus 1 by n square. This can be written less than or equal to y square plus twice y by n plus 1 by n, because 1 by n square is less than or equal to 1 by n. So this can be written as y square plus twice y plus 1 by n. Okay. Now y square is less than 2, that means 2 minus y square is greater than 0. And in the last lectures also we had done Archimedean property. So this 2 minus y square is a real number which is positive. So we can find a natural number n naught such that n naught into 2 minus y square is strictly greater than twice y plus 1. Okay, the reason for choosing is the equation 1 is in our mind. We want to make this quantity less than 2, right? So we see that it can be done because we have the Archimedean property. So by Archimedean property there exists a natural number n naught such that n naught into 2 minus y square is strictly greater than twice y plus 1. That means twice y plus 1 by n naught is strictly less than 2 minus y square. So 1 implies that y plus 1 and 1 by n naught square is strictly less than y square plus 2 minus y square. And what is that? It is less than 2. Y plus 1 by n naught square is strictly less than 2. That means what? Y plus 1 by n naught is an element inside T, because T contains all those elements whose square is less than 2, right? Supposing that y is rational, so here we are supposing that y is rational. Suppose that y is rational. Okay, so suppose that y is a rational number. So supposing that y is rational, let me write it here. Supposing y is rational. Okay. So but we arrive at a contradiction here. This contradicts. So if y is rational, so we get a rational number, or we get an element inside T which is strictly greater than y. But what was y? Y was the least upper bound. Okay, so y is the least upper bound of T, but so y is an upper bound of T, but here we have got an element which is strictly greater than y, element of T which is strictly greater than y. So this contradicts the fact that y is an upper bound, right? So this cannot happen. Y square less than 2 is not possible. Let y square greater than 2, then y minus 1 by n squared is y square minus 2 by n twice y by n plus 1 by n square. This is strictly greater than y square minus 2 twice y by n. Again we will apply Archimedean property. Since y square is greater than 2, so y square minus 2 is greater than 0. So by Archimedean property we can find a natural number n naught which satisfies n naught into y square minus 2 is strictly greater than twice y. So we have twice y by n naught is less than y square minus 2. So you multiply both sides by minus 1, we get minus twice y by n naught is strictly greater than 2 minus y square. So from above we can write y minus 1 by n naught square is strictly greater than y square minus this, which is strictly greater than 2. That means we have got 2 is strictly less than y minus 1 by n naught whole square. So we have found out a natural number which is less than this. So for any t inside capital T, we have t square less than 2. This is by definition, and here we have got that 2 is always less than this. So ultimately t is less than y minus 1 by n naught. So that means we have got a real number which is strictly less than y and is an upper bound of the set T. That is t less than y minus 1 by n naught for every t inside T. That is y minus 1 by n naught is an upper bound of T. But this again contradicts the fact that y is the least upper bound. Y is supremum of T, so it is the least upper bound. So no number less than y can be an upper bound. But here we have got that y minus 1 by n naught, which is a number less than y, and it is an upper bound of T. So that's a contradiction. So y square greater than T is also not possible. So the only possibility is that y square is equal to 2. So y cannot belong to Q, as we have already seen that square root of 2 is not a rational number. There cannot be any rational number whose square is 2. So that is, we have got a bounded set of rationals whose supremum is not rational. So Q is not order complete. Okay. So we cannot say that every non-empty bounded above set in Q has its supremum in Q. That cannot be said. So Q is not order complete. Okay, so this is the proof. Please go through the proof. It's not that difficult, but it's a very important proof and slightly confusing. Okay, it's a very important proof. So in the next class, so we are done with the properties of real numbers. In the next class, we will start with the countability and uncountability of sets, and that will end our first unit. Okay, thanks.